Catalytic hydrogenation. Alkenes, when reacted with hydrogen in the presence of palladium catalyst, it's going to get converted into alkane, where the two hydrogens are going to get added to the double bond. So 2-butane, when it undergoes catalytic hydrogenation, it's going to give us butane. Similarly, 1-methylcyclohexene is going to give us methylcyclohexane. A catalytic hydrogenation reaction is a reduction reaction because there is increased number of carbon-hydrogen bonds. The mechanism for catalytic hydrogenation is too complex. All we know is the hydrogen molecules are going to get absorbed on the metal surface, and the alkene molecule is going to form complex with the metal by overlapping its p orbitals with the vacant orbitals of the metal. We can also think that both the bonds, the pi bond from the alkene and the sigma bond from the hydrogen molecule, they both are going to break, resulting in radicals. And in the next step, these radicals, the hydrogen radical is going to combine with the carbon radical, forming sigma bonds, giving rise to our final alkane molecule. Relative stabilities of alkenes. Hydrogenation is an exothermic reaction and a huge amount of heat is released in the hydrogenation reaction. And this heat that is released in this hydrogenation reaction is called as heat of hydrogenation. The heat of hydrogenation can be related to the stabilities of alkenes. Stable alkenes will produce very low amount of heat of hydrogenation. Let's compare the stabilities of these three different alkenes. Out of these three different alkenes, this is the one that is highly substituted, and therefore this is going to be the one that's more stable. Since this is the most stable alkene, it is going to release a low heat of hydrogenation of about 26.9 kilocalories per mole. And this is the one that is least substituted across the double bond. Right? Because you have a total of 3 hydrogens, 2 hydrogens here and 1 hydrogen here across the double bond. Therefore, this is least substituted, and this is relatively unstable, and therefore it should release a high amount of heat of hydrogenation of about 30.3 kilocalories per mole. So this is the one that is most stable. This is the alkene that's most stable because it's highly substituted, and this can also be seen from its energy. This is the one that has the lowest energy of all the 3 alkenes, and therefore this is the one that's going to have the lowest heat of hydrogenation of about 26.9 kilocalories per mole. Relative stabilities of alkenes. A highly substituted alkene is said to be more stable. When you have 4 R's, then this is the highest substituted alkene, and therefore this is the one that's going to be more stable. So here in this alkene, you only have got 1 R group, and therefore this is the least stable here in this group. So with the increase in the number of R groups across the double bond, the stability of the alkenes is going to increase. The trans alkenes are in general more stable than the cis alkenes. This can be seen from the low heat of hydrogenation for the trans alkenes. When trans 2-butane is subjected to hydrogenation in the presence of hydrogen and palladium catalyst, it's going to give us butane. And for this reaction, the heat of hydrogenation is 27.6 kilocalories per mole. Whereas in the case of cis, this number has been increased to 28.6, and that is because of the low stability of cis 2-butane when compared to the trans 2-butane. Now, why should the cis isomer be comparatively unstable? That is because of the steric hindrance in the molecule. You have 2 methyl groups which are present on the adjacent carbons that is going to cause the molecule to have some sort of steric hindrance. Whereas in trans 2-butane, the 2 methyl groups are far away from each other, and therefore they are going to have minimized electronic repulsions between them. Relative stabilities of disubstituted alkenes. You can have 3 different types of disubstituted alkenes. One is the trans alkene, and the other one is the cis alkene, and the other alkene is where the 2 R groups are present on the same carbon. Okay, so between all these 3 compounds, the trans is the one which is more stable because the 2 methyl groups are far away from each other. And then comes the cis. We can expect the cis compound and this substituted alkene to be of the same stability because they both have only 2 R groups.